Let's wait for 1 more minute. After that, we will start the session. Okay, let's begin the session. Okay. So, what I have, I will give this, whatever the things in this tutorial session that will help you to solve the assignment 6, basically, and related to this network theorems and all. So, after that, we will see the last topics which were not covered in the last session, that is related to the Laplace transforms and all. So that will also give you some glimpse that how to integrate this network analysis theorems with this Laplace transform so that it can be made analysis easier. Okay. So this is the sixth tutorial session of the network analysis, and whose instructor Professor Tapas Kumar Bhattacharya sir from IIT Kharagpur. And I am Satya. I am a PMRF research scholar and Department of Energy Science and Engineering, IIT Bombay. So let's begin with the first problem because for few problems I have kept related to the network theorem. After that, we will see what is the Laplace transform, then how to integrate and solve the problems which are given in the assignment 6 basically. So this is the first problem. Network theorem means we will see some of the problems related to superposition, Thevenin, Norton, Thevenin's theorems, and also some of the compensation theorem based upon the different types. So this is the first question. Try to solve this, and if you face any difficulty solving this, just let me know. You can write in the chat box also, or you can just open your mic and also you can tell.
False.
Oh, false. Okay. Okay, I got one answer as a false. Okay. One more people is there. Take your time. Samita is there. So take your time and try to solve this problem. After that, I will give the solution for this. Okay, let me give the solution for this problem. Uh, What is asking in this question that superposition theorem in principle is not applicable to the network which contains the time varying resistors. Okay. So what we have studied in the few means in the lecture itself, professor told that superposition theorems basically where it is applicability is there. Okay. In this question, the superposition is basically mentioned. So there are a few things you should always remember that in inside of the theorems, when you read the theorems, always read the statement. Always read the statement of that means theoretical statement of that theorem. Statement of that theorem basically. Two, you will know that ki, applicability of basically where it is applicable. Applicability you can know after that. Applicability of that theorem. Why I'm saying this? Because few of the problems, if you see the superposition theorem, the linearity is one of the criteria to when you are trying to solve the superposition theorems. Okay, so the thing is, when you see the linearity, it means that it should not be a linear function. It should be a linear function of the things which are varying. Suppose I am taking one example where in this question it is mentioned that time varying registers. But what we have seen that ki register is a linear element. Okay, basically. Okay, so register is basically a linear element. The problem here is that there is a two kind of system that this register can also be a non-linear. Non-linear when? Suppose it is a time varying, temperature varying. Suppose R naught 1 plus alpha T minus T naught. So this is the R which is dependent upon the temperature because R is now the function of temperature here. So now the resistance will vary as the temperature varies. Okay. But in this question, it is saying that the time varying resistor. It could be a resistor, could be a R naught T square, kind of a one example. So basically, so if the circuit contains the time varying resistors, so this superposition theorem cannot be applicable because the linearity is being lost. So let me take one more example. After that, I will show you why I am saying that again. Because my emphasis is that it should be a constant value, otherwise its linearity should be lost. Suppose I take the one which I have taken previously that R is equal to R naught T square, which is varying with the time. Okay. So if it is varying with time, so at different time stamps, suppose I am taking T is equal to 1 second. Okay. So R will be equal to R naught. If you are taking time is equal to 2 seconds, so R will be equal to 4 R naught. So the register value cannot be same at different time stamp. That is the problem. Okay. So this is not a linear circuit. This is a non-linear circuit. Non-linear circuit. And also it's a time varying. Okay. So this is the problem that if it is resistance is time varying, then it could not be a linear circuit in these scenarios. Okay. So it is kind of true statement that it is not applicable to a network where containing the time varying resistor basically. But register, suppose I'm taking one thing that V is equal to Vm sine omega t. If the voltage is time varying, because the voltage, if you see sine is there, so voltage equation will be something like that. Here it is actually the time varying. Okay. So the thing is the voltage sources, if you are taking the AC, voltage source AC, it is a time varying at different time stamps. It is a variable, okay? But what we would usually take, it's a RMS value for the analysis, okay? Here the thing is that RMS value is fixed. RMS value is usually fixed, but the voltages at different time stamps are different, but the RMS value is fixed. So that's why for the analysis, we usually take the only RMS value for the analysis, okay? Any doubt?
So once again, sir.
Okay. So if you see in this question, what is saying that in the superposition theorem, it is asking that whether it is applicable at a in a networks where the time varying resistors are there. So time varying resistor basically means it is a basically non-linear circuit. It could be any form. R could be a function of time. Basically, it is saying. So R could be R naught T square, R naught R is equal to R naught T cube. Any equation can be applicable. Okay. But the problem here is that if you go on analysis of the superposition theorem, because the fundamental of superposition theorem is that when you have the two different more than one voltage sources, current sources, so at a time replace take one voltage source, whether it's a current source or voltage source, and replace it with its internal impedance, basically. So when the resistors which are there in the means the network, it's a time varying. So how you are going to represent and replace with them? Okay, so that is the thing. So basically, the superposition theorem basically hold when the linearity is being defined. Okay, but in this equation, in the
The
question.
superposition theorem is works under only linear elements also.
Yeah, so here the question is that resistor is there, but the resistance is time varying. So that is the problem that if it is time varying, so it could be a linear circuit and it could not be a linear circuit. But what we linearity we have seen, R is equal to R naught, which is a constant value. Okay, resistor could not be a variable, but voltage sources which we use for the analysis is RMS value basically. Okay, got my point?
Yes, sir.
Okay, so let's move to the second problem. Try to solve this. This is related to compensation theorem basically. So there is a one question in the assignment also related to compensation. If you know the theorem, just try to solve it. Try to solve the first part. It is saying in the first part that to find what is the value of current which flows through the AB branch. This is the AB branch. Once the resistance is 4 ohm, it means that 3 ohm is replaced by the 4 ohm. Then what will be the value of current which is flowing in this? Suppose this is I. So find out the value of I when it is changed from the 3 ohm to 4 ohm in this AB branch.
One 1.6 amperes, sir.
Okay, first I got 1.6 ampere. Try to solve the second one.
Sir, in assignment 6, they didn't ask anything about compensation theorems.
Yeah, that is true, but I want you guys to solve it by compensation theorem. Then we will see whether it is same with the when you go for the normal circuit operations. Okay.
What is compensation theorem, sir?
Okay, you don't know compensation. Okay, I will explain. I will explain. Okay, don't worry about that. Let's wait for one more minute. Maybe some other person can solve. After that, I will explain what is a compensation theorem. Okay, let me give the solution and also what is the basically the compensation theorem is. Okay. So first I will solve this problem with the normal method. Then I will solve with the compensation theorem. Then we will check that whether it is coming equal or not. Okay. So let's solve by the normal method. Okay. So it is asking what is the current when the resistor is 4 ohm. Okay. So let's replace. Suppose currently the 3 ohm resistor is there. Then I am drawing the new circuit with the 4 ohm resistor. 8 volt, it is 3 ohm, it is 6 ohm, okay, and this is actually 4 ohm. What is the R equivalent? R equivalent, when you see from the 8 volt source, it will be modified something like this. Okay, 3 ohm, then the equivalent of R is 4 multiplied by 6 divided by 10. It will come out to be 2.4. This is 2.4. So overall current which will flow, I total will be 8 divided by 3 plus 2.4. It will be equal to 8 divided by 5.4. Okay. So what is the value of current which will flow through the 4 ohm resistor? So when you see the current which is flowing here, suppose this is I total. So in the 4 ohm, it will be I multiplied by 6 divided by 6 plus 4. Basically, it will become I multiplied by 6 divided by 10. What we have got? We have got 8 divided by 5.4 multiplied by 6 divided by 10. Let's solve it. It is coming 8 multiplied by 6 divided by 10 divided by
Sir,
5.4. Yeah,
I total will be 8 by 3, na, sir. V by R.
V by R. That is true. 8 volt is given, 3 is given here, and when you replace the resistor with the 4 ohm, currently it is 4 ohm, so 6 multiplied by 4 divided by 10, it will become 2.4 here, and then 3 plus 2, it becomes 5.4. So I total will be 8 divided by 5.4. Because the current, because we have drawn this is the parallel form, no? So we have converted its equivalent. R equivalent will be R1 R2 divided by R1 plus R2.
I total, I total is passing through 3 ohm resistance, na, sir.
Yeah, that is true. But when you need this equivalent also, na? This R equivalent. So this is the R equivalent basically for finding out the what is
Can't
the
we
current.
write,
Yeah.
can't we write I is equal to that 8 ohm by R3 because I total is passing through the 3 ohm
No, no,
resistance.
no, no. This is the problem. No, no. Let me explain why. So the thing is, suppose this is a voltage source. Suppose this is a 8 volt and 3 ohm is given here. Okay. And one more thing is given here, that is 6 ohm here, and this is the 4 ohm basically. So for finding out what is the value of current, okay, for finding this current, you need the voltage across this and also the voltage across this also, okay? Because when you apply the KVL, suppose this is the voltage V and this is the voltage V dash. So when you apply the KVL here, so it will become minus 8. plus V plus V dash is equal to 0. So here if you see the V plus V dash is equal to 8. Okay. So it means that whatever the voltage which is appearing here, let me take any other pen. Suppose I am taking here, if you see the 8 volt, this whole voltage will be appearing across this circuit. Okay. So the finding or for finding the current across the this 4 ohm, you need the what is the voltage across that. Okay. So these two are in the parallel for finding the voltage. Suppose I wanted to take the what is the value of V dash. So what will be the value of V dash when you try to solve it? So V dash will be equal to I multiplied by, because the I what is current. Suppose the I current is coming here. So it will be divided into the two circuit. It is I dash and I double dash. So basically I multiplied by I dash multiplied by 4 plus I double dash multiplied by 6. Getting my point? So I dash multiplied by 4 plus I double dash multiplied by 6. So this is the overall voltage of V dash. Okay. So that is being used to solve here.
Voltage is, voltage is same across parallel sir. We can take anything I dash into 4 or I
Yeah, that
dash
is
into
true.
6.
That is true. That is true. That is true. What I'm saying that suppose this is the circuit here. Suppose 6 ohm is here, 4 ohm is here. Okay. So the voltage across this is same. This is the V dash, no? So that is same voltage will appear here across the 6 ohm also. That will appear the 4 ohm also. This voltage is actually same. But the what I am telling, this V dash. Okay, okay. I think, but what is the value of V dash? V dash will be equal to I dash. Oh, here I done one mistake here. That is true. V dash will be equal to I dash multiplied by 6 equal to I double dash multiplied by 4. That is true because the voltage will be appearing across the both circuits. So for finding out the V dash value or I dash value, need to know the V dash. Okay. Or you can simply say that V dash will be equal to I, which is flowing at this terminal I, and this are equivalent because it is going into the network. So IR equivalent value will be the same as the what the voltages across appearing the 4I double dash and 6I dash. Okay. So it will be equal,
Yes.
getting my point. So R equivalent will become 4 multiplied by 6, 4 plus 6, that is 10. Okay. So this is the thing. Why? Because the you have to take the R equivalent also into the picture while finding out this current that we have find it out from here. Okay. So that is coming actually 0.88. Okay. So
Yes, yes.
let's try to solve it by compensation theorem. What the compensation theorem says that when the circuit inside of the voltage source and the where you wanted to find out the current, it should be linear. Suppose uh, this circuit, if you see this circuit inside of that, it can be represented like this. So here the voltage 8-volt source is there, and after that one resistor is connected. Suppose the R is connected, and this is the inside network. Initially it was 3 ohm.
So, what is the difference between network and circuits, sir?
Oh, circuit is basically when you see means circuit basically the when the two elements are there. When you go from more than two elements, when you go from the greater than two elements, so it will become basically a network. And the network also consists of the dependent or independent sources as well. Maybe because network have to be some source and sinks could be there. Getting my point? That's why you can say that ki if the elements varies, when the two elements are there, it is kind of circuit. When you go with the higher number of elements into the circuit, then it will become a network with a voltage sources and all, voltage sources, current sources. And all. Getting my point? But
Then how? Then it's there's only two elements in that network, na sir, 3 ohm and 6 ohm.
yeah, that is true. That what I am drawing now. this is actually this. I wanted to simplify the analysis, not simplify the analysis. Basically, I wanted to draw this circuit in a very small manner. Means try to give you a glimpse of compensation theorem in a easier way. Okay. So this is the network which I have considered with the, I have assumed that this is a kind of network which is similar to that. That is a 8 volt, and inside of that there is a network. Network means this is the parallel series in the with the 8 ohm and 3 ohm in the parallel with the 6 ohm. That is actually a network inside, and there is a one resistor at the end. That is the 3 ohm. Getting my point? This is just a representation form.
Yes, sir.
Okay, you don't have to bother about that. You just focus on the what is actually the theorem is. Okay, this is just the way which I am representing and try to give you glimpse of the what is actually the theorem is. Okay, so this is the one circuit. So what the compensation theorem says that when the resistor is being changed, suppose this is a 8 volt and this is actually the network, and network is being constant in the both circuit when you are replacing it with the 4 ohm. Okay, so you can actually draw this circuit as simply like this: 8 ohm volt in between the network, the same network, and replace this 4 ohm with the resistance change. What they mean by the resistance change? That is the delta R. Replace this resistor with a voltage source whose value is V is equal to I delta Z. This I will explain what is the value meaning of this I. Delta Z means what is the new value and what was the previous value. And this theorem is also applicable only in the linear circuit. When the network inside of that, in the inside of the network, the circuit is actually linear circuits. Resistors are there, voltage sources are there, kind of. So you should replace this with the I delta Z. Then the resistance, what was the new value? New here is the 4 ohm. Okay?
9 ohms, sir.
No, no, no. I am talking about the first problem only. I am trying to solve the first problem with the compensation, basically. Then we will
Okay,
verify
sir.
whether the current which we have found it out 0.8 something, whether it is correct or not. Okay, 0.88. So here if you see current we have got initially with the 4 ohm resistor was 0.88. So here the thing how to find out the value of I. I is actually the value of current when the circuit was 3 ohm. This is the previous value of the current. Okay, getting my point. So
Yes.
you don't have to bother about that what is the current which is flowing into the circuit with when the theorems are there. You just have to replace the things with that and try to find out what is the value of current. Let's solve with that this theorem. The this Let's solve this problem with this theorem. Then after that we just see that whether it is coming correct or not. Let's see. So this was the circuit initially. It was 8 volt, and then the inside circuit was 3 ohm. Then the circuit was 6 ohm. Then we wanted to find out what is the value of current basically when the changes were there. So what we have done, we have replaced this with the 4 ohm and with some current sources and all. Okay. So theorem says that basically the what when you find it out the what is the value of voltages across that. Okay. So what is the value of current basically? Let's try to solve that. This was the voltage. That's 4. When we have replaced, it will become 1 volt. Okay. Okay, got it. Then try to solve what is the value of new current here, I, which needed to be find it out. So when you apply the KVL or something KCL here, so it will become something V minus 8 by 3 plus V by 6 plus something V minus 1 by 4. So by finding out the what is the value of V, you will able to find out what is the value of current here. So the basic property means what I wanted to say you that when you try to solve and apply the compensation theorem, try to solve it by something like that. When replace the resistor which was there initially with a voltage source which whose value is I delta Z.
How 1 volt, sir?
Yeah, this is actually sorry, not 1 volt. This is basically the I delta Z. I delta Z. So it is not 1 volt. This is actually value of I. Delta Z was so current you have to find out what is the initially what was there with the 3 ohm. Then you have to replace it by I delta Z and this with this R new. Then you will able to find out what is the value of new current across that. Okay. So there is a one more theorem that by that you can use that is called as Telengen's theorem. Okay. So in that theorem, what it says that when the source and sinks are not being replaced, suppose it means that suppose the source was there here and inside the network was there and the resistor was there at the end. Okay, R. So suppose this is V and suppose the current which is flowing here is the I. Okay. So here the R was there. So when you replace this circuit by the like this, suppose the resistor now I have connected like this here, and the voltage source here we have connected. Okay. So here also the what the current which is flowing here, suppose this is I dash. So I dash will be also equal to V by R. And here also I was equal to V by R, kind of. The ratio basically, the ratio will be become same. It could be anything. Suppose the V1 and here also V2 was there. So ratio of V1 V2 could be the same. Okay. So when you apply, suppose I wanted to apply here that theorem. So 8 by 3 divided by because the voltage is being constant whenever the we have changed the circuit. But here in the sink side, if you see the resistance and the second voltages come into the picture. So that's why it was not applicable here. If you see here in the new theorem. Okay. Are you getting my point? How to apply this compensation theorem and what is the meaning of this Telenges theorem? Are you getting what I am saying? Should I explain again?
Once again, sir.
Okay, let me explain again. What I am telling, when you see the network inside of that, when it is a linear circuit, when you wanted to find out what is the current when it is being changed from one resistor value to the other resistor value, in that circuit, you just have to see that what is the current which is flowing in the other circuit and you have to replace that with the V is equal to V dash. That is actually the correct way to finding out the value of what is the value of current across that. What I'm saying that suppose this is the network and there is a some voltage source here V and one resistor is connected. Okay, R. Now what I have done, I have replaced this R with the I plus delta R plus delta R. Then the theorem says that this keep this voltage as a constant, whatever was there, and network, and then replace this R with the register what was the new. New means what is the value new? R plus delta R, and then add a voltage source whose value is equal to I, which was the current which is flowing initially, multiplied by delta R. Okay. After that, you will be able to find out what is the value of here the current basically. Are you getting my point? So how to replace that? So that is the thing. How you will be able to solve that problem. Getting my point?
Then how to find current in the new resistors, sir?
What do you mean? What you're saying?
We found voltage. We have connected voltage source and new resistor. Then how to find that current in the new resistors?
Okay. So what I'm telling in the new register basically the I was there, no? So now it could be I dash basically. Okay. So now the I dash will be, suppose this was the network initially. This was the network. So now I have replaced this 3 with some voltage source here, and then I have replaced with the 4 ohm new resistor. Okay. And here the current was, suppose the I, it is coming something, and then the delta change is the 1 ohm. Then you have to solve this circuit, this 6 ohm, and then the 8 ohm, 8 volt basically, and find out what is the value of current. That current with I dash will be actually the current which is coming, the change basically R, I. What could be the value of current which is flowing through the 4 ohm basically. So it is a kind of not coming simplified form in the lower circuit, but it is make the simple system basically very easier when it is a larger networks are there. So then when you are replacing with resistor there with this voltage sources and all, then it become very easier to solve with this compensation theorem. They in the assignments also there are one question is there. Okay, try to solve with this method, then find it out because it is you can solve this network by the easier KVL and the KCL also. That is not a big deal. But if it is specifically being mentioned whether it is solved with the compensation theorem, network Thevenin theorem, superposition theorem, then try to use that methodology to solve that network. Okay?
If they ask to solve using compensation theorem, uh, can we solve through KVL theorem? Is the
Yeah, yeah,
answer to both
yeah.
theorems, sir?
Answer will be the same. If it is an objective question, try to solve it by network only. Okay? So then you will get the correct answer and also in the less time. But when the network is very large, then the compensation theorem become easier because you don't have to see the inside of the network because 3 ohm, 6 ohm you have to solve currently. But when the bigger networks are there, then at that time the voltages across that sometimes given. Okay. So and that time frame you can just find out. Suppose here the 3 ohm, the question would be like this: कि voltage became 8 volt when it is being or 6 volt when it is replaced with the 9 ohm. Then after that you will see that we have replaced with this 4 ohm and also you know the voltage. Okay. So in this type of question it become very easier to solve what is the value of current, new current. Okay. But in this
So
type,
here I dash new current is that voltage
yeah,
into
yeah,
four.
yeah,
Okay, sir.
that is actually the new current. Okay.
Yes, sir.
Okay, let's move to the Thevenin part, Norton part. Then after that, we will see the Laplace forms and all. Try to solve this problem with the Norton equivalent.
Sir, in compensation theorem, if they ask, uh, will they ask new resistance is 4 ohm, old
Mm.
resistance is 3 ohm? Will it be for a voltage source also, sir? Will they ask like that for voltage source?
No, no,
New
no,
voltage source
no,
is
no.
6 volt.
It could be asked whether what is the coming the voltage across that resistor, new voltage. Then you will able to find out because you are replacing that with the resistor only, now the voltage source and new resistance. That is actually a replacement of the resistance change only. So just when you find out the current, new current, just multiply it by the new resistor, you will get the voltage across that branch.
Mm. Okay, so then what's Telegrand's theorem, sir?
Telegas theorem, basically a power. Uh, it is basically like this. Suppose the what is the law of conservation power? What is the power which is being absorbed is actually equal to what is power being given. Okay. Suppose this is a smaller network is there, this kind of. So whatever the voltage power given by this voltage source, that is only the power which is absorbed by this R1 and R2. That is actually net of power is equal to zero. Okay, so this is a kind of Telenga's theorem. What it actually give you. Okay, so
Yes.
okay, in the slides also, professor had talked about this Telenga's theorem and also this compensation theorem. Try to go through that, the derivations and all. You will get the feel of that. Okay, try to solve this problem, that network problem. Okay, I got one answer as IN is equal to 1 amps and RN is equal to 4.5. Anybody who don't know this theorem basically, if you don't know, just let me know. I will try to resolve, make you understand that what is actually the Norton equivalent.
Don't know, sir.
Okay, I will explain that. Let some other person also to solve. After that, we will discuss.
Okay, sir.
Yeah. Okay, let me explain what is actually the Norton theorem is. So if you see that this network is linear. There is a current source is there, basically DC current source, and here also 6 volt source is there, and this is a 3 ohm, 3 ohm, 3 ohm. So all the things,
All these things are leaders.
yeah, yeah, these are the linear element basically. So this
And
theorem,
AC sources are non-linear, sir.
no, what I have told na, ki in the linearity, we will define because the if you the volt AC sources sine omega t is there. Okay, so this is actually the time varying, but what we use for the analysis basically the RMS value. Here we use basically the 6 by root 2 angle of something, suppose 0 degree we have taken. So this value, RMS value is fixed, but the instantaneous value is varied. What that we don't take in for the analysis. We just find out what is the value of RMS, then we will convert into the time domain. Okay. So that don't come into the picture, that variability. Only we used to say that what is the RMS value and how the RMS value is whether it is fixed or not. Getting my point?
If RMS value is fixed, then it's not linear, sir.
Yeah, linearity basically being means circuit usually being solved with this RMS values. Okay. Okay, so these are the kind of linear circuit and it also DC. DC is actually not time varying. So DC is actually constant. And also the current also it is usually constant. So this is not a time varying circuit. So and when you see that applicability of Norton equivalent theorem, what it says that suppose some network is there, you can replace that network with a current source wh- which is called as a Norton current and one resistor which is actually Rn in parallel to that. Okay, so you can convert, suppose this is the AB terminal, A here and B here. So this whole circuit can be converted into a current source and a parallel resistance. Then how to find out? Now the next question is how to find out how to find Rn and In basically. So now the thing is for finding the for finding In, just short circuit the AB terminal. You have to just short circuit this AB terminal, okay? Or and in the better way to say that, replace it with a internal impedance. Now, because I'm assuming that this is Norton equivalent is an ideal circuit, so just sort it out, sort, then find the value of current here, IN. Now the circuit, how it will be look like? It will look like something like this: 6 volt, 3 ohm here, 3 ohm here, and when it is get short circuited, then it will become something like this: 3 ohm here, 3, and then this is the 2 amps. It is connected, and this will become something like. So what I wanted to find out, what is the value of current here? Okay, so this is also 3 ohm. Okay, so this is the how to find it out, the value of IN basically. Now the second thing is, in these situations also, for finding out the what is the value of IN, you see that there are different sources are there. Then you have to apply the KVL and KCL based upon that. Okay. Now the second question is that how to find for finding the value of Rn, that is the Norton equivalent. For finding the value of Rn, if the voltage sources are there, replace it with the internal impedance. Here the DC source is there, there is no impedance is being given. So assume it as a short circuited, then 3 ohm, then 3 ohm, and then open circuit the current sources. Suppose here the 2 amps are there, so just open circuit it, and here you can connect this resistor here, and then R equivalent from here, if you see that.
How to find the internal impedance
It will be
in the circuit,
it,
sir?
it will be given. Suppose in the question, if it is saying that there is a 6-volt voltage source with an internal impedance or internal resistance of 3 ohm, and but it is not being shown inside of the circuit, then you have to assume that it is not a ideal, and you have to replace. Suppose let me give you one example here. Suppose what I am saying that, suppose there is a one DC source, 6 volt, and some resistor and some connection source are there. Suppose this is a kind of circuit is there. And in the question it is saying 6-volt source has internal resistance of 2 ohm, but it is not being shown inside of the circuit. Here if you see, it is like this: 6 volt and also one resistor in 2 ohm, but it is being shown like this, and but in the question it is being written. Okay, then you have to assume that circuit, this DC source will be something like this, not the just a DC source. Getting my point? So it will be specifically mentioned in the question that what is the internal resistance. If it is not mentioned, suppose in the question it says that 6-volt source. Okay, there is no mention of the internal impedance. Okay, so in this scenario there will be two cases. Suppose the voltage source is there and the current source is there. So how we represent the voltage source? One source voltage and one resistor in series. How we represent the current source means practical current source, current I, and one resistor in parallel. Okay, suppose this is R, this is R.
Yes,
Okay.
sir.
Okay. So then in these situations, if it is specifically mentioned that the internal resistances are 2 ohm, 3 ohm something, then replace that voltage source. When you sort this also, this sort also, then the R will come into the picture. But here if you see, here you if you open circuit this current source, then also this R will come into the picture. Basically, simple saying that replace this current source as an open circuit, replace the voltage source with a short circuit. Then the internal resistance are there. If it is not given the R, then the R will be 0 here and R will be infinite here. Just see what I'm saying that If it is not mentioned, R is infinite here. In the current source, R is equal to 0 in this. Okay, so that's why it is a kind of open circuited system. Okay, so it will be open circuited from resistor also, open circuited from the current also. So the circuit will look like it's just a open circuited path. Getting my point? Because the R is infinite. So that is the thing why we replace with this, and it will be specifically mentioned in the question. Okay. Let's try to solve what is the coming the R equivalent. First R equivalent Rn will be equal to, because this 3 ohm and this 3 ohm is in parallel and it is coming in series with this 3 ohm. See from this point. So 3 ohm, then this 3 ohm and 3 ohm is in parallel. So 3 ohm, this 3 ohm plus 3 ohm in the parallel, 3 multiplied by 3, 6 here. So it will come out to be 4.5. Getting my point? So 4.5 is the Rn value. Let's find it out the value of I. Let's try to solve it. You should also try it by just watch what I am how I am solving. Then after that you should solve at home also, so that you can feel that what is the value of Rn, what is the value of In, how it is coming. Let's try to find out the value of I. This I. Let's draw the circuit. This is actually the 6 volt which was given. And then what we have done, we have actually the sorted the path. Then it became something like this. 3 ohm was there here, and 3 ohm was there here, and then we have one 3 ohm here, and then the current source here. What is the value of current source? Current source is 2 amps. It is connected, and this is the value of IL. Okay, so let's apply the KVL, KCL basically. Let's apply the KCL. Let's take it as a ground, and this is the voltage V. Okay. So when you see that this is a voltage V, what I have told in the previous classes also, always assume that the current is leaving from that node. So I will assume that the current is leaving from that node, and after that the summation of I will be 0. Let's apply that. V minus 6 by 3 plus V by 3 plus V, because it is 0 potential. So V divided by 3 plus the current is going. This is 2 ampere is going out of the network. So this is a kind of this. Okay. Any doubt in this? No doubt. So let's try to solve it further. So when you take the LCM, what it become? It will become V minus 6 plus V plus V plus 6 divided by 3 is equal to 0. And it will come out to be 3V, and 6 will be get cancelled out. That is a new thing. Okay, when you see that 6 is getting cancelled out, when what we have done, V minus 6 by 3, V by 3, V by 3 here, V by 3 here, and the 2 amps here. When you solve it, it is coming 3V is equal to 0, V is equal to 0, which means that this V is actually a 0 potential, and this was also 0 potential. So what is the value of IN? There will be no current. Okay, it means that all the points are being connected at the same potential. So the current usually will be equal to V minus 0 by something. What is the value of impedance here? But when the voltage is itself is a 0, whatever the impedance inside of the network, current will be 0. So now the IN is became 0. So how it will be represented? Something like this. Current source basically here, and it is 0 amps. But the Rn which we have got, if you see here in this circuit, what we have got, the R value, R equivalent, which we have solved, that is 4.5. Getting my point? So in this type of questions, you have to see whether what is coming, whatever the value in this question, the 0 is coming. So it will be the case that 0 amp will can be flow into the circuit also. Getting my point? So it is a kind of 0 amps and the 4.1, the equivalent could be looking like this. So it getting compensated by the voltage source and the current. Any doubt in this?
How can 0 ampere flow, sir?
No, 0 ampere is there is a means that it is a kind of open circuited system, no current is flowing. So after the when we have applied the KCL, this voltage here, it is coming zero. Okay, so then we are in the confusion that what is the amount of current which is flowing here, because this is the value of RN basically. Let me take the color here. Suppose this is wanted why we wanted to find out what is the value of IN here. But the voltages here is also zero, here is also zero. So it means that they are at a same potential. It means that it is actually connected network. Okay, so that's why the opposite path will don't have any current. Suppose this is a one voltage source, 6 volt, and this is the one resistor here, and one resistor connected here, and here one resistor. And suppose when it is get short circuited, so all the current will flow here. Short circuited means it is connected at the same potential. Whatever the potential was here, the same potential will be reflected here. So all current will flow from this circuit. That's why there will be no current through here Rn. And it was already zero. So that's why the current is equal to 0 minus 0 divided whatever the value of R, it, it will be always 0. Getting my point?
If it's short circuit means current will be infinite, na? So voltage will be zero and current will be infinite.
Yes, yes, that is true for this line, not for this line. I'm talking about this line. Because in the question, what we have got, this has a zero potential, this is also zero potential. What I am telling that this is a path which have certain resistances or not. Okay. So, but they are at the same potential, so there will be no current flowing into the network. When suppose this is a 2 points, this is also at a zero potential, this is also zero potential. This is also grounded, this is also grounded. So what amount of current will flow into the circuit? There will be no current. Why? Because there is same potential. When it is a 2 volt and this is a kind of 1 volt, then the current only flow there. No, I is equal to 2 minus 1 by something internal resistance when it is there. But here the potential which is coming, here also zero, here is also zero. It means that there will be no current, whatever could be the value of R here. Okay, getting my point. Here the two kind of things can happen, that this is 3 ohm inside of that, but there will be no current because they are at the same potential. This is also zero, this is also zero. Inside of that 3 ohm is there. No current will flow. And same with the other form also, others means circuit also. This also, this also, this also. No current will flow because they are at the same potential. For the current to flow, one node should be at a higher potential, other node should be a some kind of lower voltages.
Yes, sir.
Getting my point? So, so that is the thing. Okay, let's try to solve this problem. So this is a kind of Thevenin theorem. Okay, if you know the Thevenin theorem, try to solve it. After that, we will discuss it. What is the kind, how to solve with this Thevenin theorems and all.
We'll use Thevenin theorem for load. voltage source and Norton theorem for a current source, na sir?
Yes, and though both theorems are a dual of each other, means when you know the Thevenin equivalent, you can draw the Norton equivalent, and also when you know the Norton equivalent, you can draw the Thevenin equivalent. This is a kind of dual nature. From one, you can find it out the second.
These theorems are used to reduce the circuit or simplify the circuits.
Exactly, exactly. They simplify the analysis basically. Let's wait for 1 more minute. After that, I will give the solution. Okay, let me give the solution for this. And first of all, let's see what is actually the Thevenin theorem is. We will do a comparative analysis. Here I am writing what is the Norton. Here I am writing what is Thevenin. Okay. So both circuits are actually, both theorems are applicable when the circuit is linear. first thing. Second thing, the equivalent circuits. So in the equivalent, the Norton is actually shown like this: IN and in parallel with the RN, what I have told the value of RN. In this, the Thevenin, it is something like this. A voltage source will be there, that is known as the VTH, and there will be RTH, and this is the equivalent. Third thing is that how to find out the IN value. What I have told, replace the R where you wanted to find out, you wanted to find IN by 0. Hmm. Means kind of short circuited. Okay. Third, here in the Thevenin, we usually find the value of VTH. In this, where you wanted to find out the value of VTH, just open circuit it. Okay. And then find it out the value of VTH across that. Okay. Fourth thing about the finding out the what is the value of RTH. What I have told in the RTH, replace the voltage source and
RNs.
sorry, RN. Basically RN here and RTH here both are same. Okay. So there is no difference between the RN here, the RTH, the same methodology. And also the value will come same. Okay. Here you have to replace the voltage source with their internal means impedances and the current source also with their internal impedances. Here also RTH also you have to replace the voltage source with their internal impedance and also the current source with their internal impedance. So this is a kind of comparative analysis. In one Norton we find out the value of IN and in Thevenin we find it out the value of VTH. Okay, and also what I have told, both are dual of each other. Both are dual of each other. It means that suppose I know the value of VTH and wanted to find out the value of IN, Norton equivalent, then it will be equal to IN will be equal to VTH divided by RTH. Okay, or RN. Basically, RTH is equal to RN, the same value. And if you know the IN value and wanted to find out the value of VTH, it will be equal to IN multiplied by RTH. Okay, so this means that from if you know the one theorem or wanted to find out the one parameter, you can find out the second parameter by just multiplying the voltages and current based upon that what you is being asked. Okay, let's try to solve this problem. Let's try to solve the problem whatever the concept which I have give. In the question it is saying there is a terminal A and B and can be reduced to a equivalent circuit of a single voltage source in series with a single resistor. It means that it is talking about there will be a one voltage source in series with the some resistor. Okay, it means this circuit will be replaced something like this. Okay, so this is actually the equivalent circuit of Thevenin. Okay, Thevenin equivalent circuit basically. Okay, it is asking then what is the value of parameters? Will be the value of V and what is the value of R? Okay, let's find it out. So step one, let's find out the value of VTH. In the VTH, what I have told, you just have to open circuit. Here already open circuited because it is being asked what is the voltage here. If it is a one resistor here, then you have to replace it. Okay, replace it by this resistor with the open circuit, then find it out the value of VTH here. How the circuit is looking like? Circuit is looking like something like this. 6 ohm is there, and this is the A, this is B, and this is the 4 ohm, and this is the 5 volt. Let's find the what is the value of across the VAB. Okay. So if you see that because here it is open circuited, so the current will flow only inside of the circuit. How the current will flow? Current will flow like this because there will be open circuited, so no current will flow outside. So it will be 0 amps. Okay. So what will be the current which is flowing here? Suppose this is I. So I will be equal to 10 because it's at a higher potential, minus 5 because it's a lower potential, divided by what is the inside of the currents resistances are there. That is the 6 plus 4, that is 10. It will be equal to 5 divided by 10 is equal to 0.5 amps. Got the point? That key 5 amps, 0.5 amps current will flow from 10 volt to 5 volt. Okay. Now if you see, you wanted to find out the value of VAB. That is the same potential across these two nodes also. That same potential across the two nodes also because they are in the parallel. Okay. Let's find out. Suppose I am taking this circuit, this actually branch, and this is also VAB. This is also A at a potential A. This is also at a potential B. And the current which is flowing inside of that, the 0.5 amp. So what is the value of VAB or VTH basically? It will be equal to zero point 0.5 multiplied by 4 plus 5. It will be equal to 7 volt. Okay. So any doubt in this? Any doubt in finding out the value of VTH?
So current in a loop is zero on sir.
No, no, no. When you see,
Voltage in a loop is zero.
suppose this is the loop, leave everything. Suppose leave everything what I have told. Let's apply the KCL here. What in the most of the cases what I have told, just ground it out here and apply KCL here and assume that current is out of that circuit. Okay, so let's apply the KCL because here the current is 0 because it's a open circuited, no current will flow. So it's a 0 plus, suppose this is V. So V minus 10 by 6, this will be current going into this network plus V minus 5 divided by 4. This will be the current which is flowing here. Let's solve. What it come out to be? 4V minus 40 plus 6V minus 30 is equal to 0. Okay. 10V is equal to 70 and V will be equal to 7 volt. Getting my point? So there will be current which is flowing from the higher potential to the lower potential side, which from the same methodology, applying the KCL also, we have got the same value of the voltages what we have found it out from the other method also. Getting my point?
I have applied KVL, sir, in that loop
Yes,
is
KVL,
equal to
yeah,
zero.
KVL will be equal to 0. Summation of V will be equal to 0 when you apply in this loop. That is true. That is true.
And I got current is 0.5, 5 by 2 I got, sir.
Current you have got. Current means this current, this loop current?
Yes, sir.
No. Let's find it out through the KVL. Let's take the one new slide. Let's duplicate it. Let me take one new slide and after that let me see. So this is the actually the network. Plus minus 10 volt was there. 10 volt was there. And here one resistor was there. And here one resistor. And here one source is there. 5 volt. What was the impedance is 6 ohm, 4 ohm. And this was the circuit. So let's apply. So this is A, this is B. Let's apply the KVL. Okay. So KVL says a summation of V is equal to 0. Let's assume that the current I flows here. Suppose this is the current I flow here. So let's apply the KVL in this circuit. Let me take any other pen. So the current flowing here, I, same current will coming here, I. So the voltage drop, this is the positive and this is negative because it's entering the 6 ohms. And then after if you see, this is the current entering the 4 ohm because it's basically a draw. Let's apply. Let's taking with the first terms. Okay. What will be the value of here voltage? 6 multiplied by I here plus minus 10 in the other I multiplied by 4 plus 5 is equal to 0. What is coming here? 10I is equal to 10 minus 5. I is equal to 0.5 amps. That is true. What we have got here also, 0.5 amps. That is also true. Okay, the theorems will be always same. That is the KVL or the KCL. What we have got from the KVL also, that is same. What we have got from the simple the KCL itself. Getting my point? And the when you find out the what is the voltage across this, that is simply the current which is flowing here, 4 ohm. That is actually the 0.5 multiplied by 4 plus 5 volt here. It is equal to 2 plus 5 is equal to 7. So that is actually the 7 volt which we have got as a VTH. Getting my point? Any doubt?
Sir, if we found the voltage across 10 volt and 6 ohm,
Yeah.
uh, will 6 into I 10 minus 6I or 10 plus 6I, sir?
So there is a one rule. There is a one rule what generally being said that when you are moving into the loop, suppose this is the loop in which you are moving, you can take the first terminal, first means positive or negative, first terminal what is coming into the picture, and then use that convention in the other form as well. Suppose I am moving from this direction, I will take the first one. What I taken plus 6 multiplied by I, and other when we went to the voltage source, it is actually the minus 10 plus 4 multiplied by I plus 5 is equal to 0. This is the one way. You can also take the negative also. Let's take the minus also. Minus 6 multiplied by I. Opposite side of the 10 volt is plus 10. Opposite side of the 4 multiplied by I. Opposite side of 5 volt is minus 5. If you see the both equation, they both are same, just multiplied by the minus. Okay, there will be no change into that. So follow the one convention that will make your calculation basically smooth forward, and use that in the all sense. What I have told in the that also one theorem, that is summation of I is equal to 0, KCL. When applying at a node, always assume that the current is leaving that node. I always follow that convention only and get the correct result in the all the situations. Just follow one
Okay,
convention.
okay, sir.
Okay, follow one convention and move forward with that. Okay, so let's find it out the value of here, the value of RTH. Let's find out the value of RTH in this problem.
2.4.
Okay, one answer got 2.4. Okay, let me check in the chat box also. Nobody has given the answer. Okay, let me solve this. What I have told, replace the voltage sources by their internal impedances. Here in this question, it is not given anything. So in the voltage sources, what I have told, always assume that the series resistance, what could be came into the picture with the voltage source, it is 0. So how the circuit will look like? Circuit will look like something like this. This is short circuited. So this is 6 ohm, and also in the opposite side, this is 4 ohm, this circuit, and other point is also 5 volt is short circuited. So when you see across the AB from here itself, so these both are in the parallel. So RTH will be equal to 4 multiplied by 6 divided by 6 plus 4 is equal to 2.4 ohm. Okay, so the correct answer is the B option. Any doubt in finding out the Norton equivalent and Thevenin equivalent? Any doubt?
No, sir.
Okay, so let's move forward. Let's try to see and test your knowledge, what you have learned. Try to find out the VAB, that Thevenin voltage across the AB terminal. Okay, I got one answer from Vishnu, that is minus 1.5. Let's wait for some other people also to give. Let's wait for one more minute. Okay, let me give the solution for this. This simple problem, just you have to see what I have told in the previous uh, questions itself. For finding the VTH across this terminal, what I have told, it is already open circuited. If it could be a resistance, then you have to replace it with the open circuit. So how to find this? So whatever the voltage appearing across the AB, that same voltage will appear across the 10 ohm also. Okay. So let's ground it here and find it out. The try to solve means apply the KCL here at the node A. Okay. So the current will at a node A will be equal to 0. In the previous questions also I have told always assume that the current is going out of that network. Okay. And one more thing here you have to see here. What I have told when you are converting from a Norton equivalent to the Thevenin equivalent or Thevenin equivalent to the Norton equivalent. Okay. Suppose you have a current source here and there is a parallel resistance is there. Okay. And suppose this is current I, this is R here. In this situation, you can convert this whole current source circuit into a voltage source whose resistance in series with a resistance whose resistance will be equal to same R and whose voltage will be equal to I multiplied by R. That is basically IR. Okay, this theorem is applicable everywhere. That is same with the Norton and Thevenin equivalent transfer also. When it is a I Norton, R Norton, there also that VTH. So VTH will be I Norton multiplied by RN. That will be equal to here RN also. So this is a kind of duality. This is called as a duality. From one system you can convert the system. So if you see in this circuit, this duality is applicable. Okay. See this circuit here. So let me to make it here. So if you see this circuit, this is similar to this. Okay. And you can convert it into the form of this. Let's convert. Let's convert. After conversion, what it could be? Always see the tip. Tip is always positive. Tip is always considered as a positive. That's why here I have taken it as a positive. But in this question, if you see, the tip is negative in the downward direction. So tip here means tip is positive here and negative here. What will be the value of voltage? Voltage will be equal to 6 multiplied by 5 is equal to 30 volt. And what is the value of resistor? Resistor will be equal to same value and the 5 ohm. Okay. So now how the circuit will look like? Circuit will look like something like this. So this will be means dual circuit, and after that this 10 ohm is there, and after that this is the VAB here, VAB here, and this is A, this is B, and then the 10 ohm is there, and then after that 10 ohm is there, and then the 16 volt is there. Okay. Now I can apply the KCL here at a point A because it is became easier. When you have the previous circuit, you have to know this potential here to find out the what is the current flowing out of that network. Okay. Now here you don't need the voltage here. You have know the voltage here. Let's apply the KCL here at a node A. Suppose the I am assuming that the voltage here is there and this is grounded. So this V and this is 30 volt and it here it is negative. So it is minus of 30 divided by what is the series resistance, that is 15. So the current flowing in this network is this plus V divided by 10, that is the current flowing, plus V minus 16 divided by 10 is equal to 0. Getting my point? Let's apply the means take the LCM and all. When you take the LCM, what it will become? It will become here 30 in the denominator. It will become 2V plus 30 plus 3V plus 3V minus 16th of 48 is equal to 0. When you solve it, 3, 3, 6, 7, 8. 8V will be equal to uh, 48 minus 60. It will come out to be minus 12. V will be equal to minus 12 by 8. When you solve, it will come out to be minus 1.5. Okay. So this is a simple way when you are facing problem in applying the KCL at a particular node. Always it should come in your mind that whether I can convert that circuit in a simpler form, whether it is a dual can be there or not, equivalent can be calculated or not. Okay. Any doubt in this problem?
No, sir.
Okay. So that is that is basically things to solve. Let's try to take the one simple problem in this format of the Thevenin and Norton. After that, we will move to the Laplace with a quick revision of the Laplace. Try to solve this problem. You just have to find out what is the Norton equivalent. Only the eigenvalue. Try to solve it quickly and use the same methodology. If you see here, this is a voltage source in connected with the resistor. Convert in a current source, it will become a simpler form. This is a hint. Try to solve.
So they have given voltage source and it's 2.5 ohm.
Yeah, this is 2.5 ohm.
It's internal impedance.
No, here there is a one error in the question. Here the question is that this is a 2.4 volt. This is not ohm. There is one mistake in the question. Now solve. Okay, let me give the solution for this because we have to move to the Laplace transform also. I will give you some of the hints to solve the assignment 5, assignment 6. So, if you see in this problem, when you find it out the value of Norton equivalent source, in this situation you have to sort it, sort here basically, and then find out the what is value of IM. Okay. So, if you see the 5 ohm resistor and this is the RN and both are in parallel. Okay, so this is something like this. This is one resistor and other parallel path is short circuited. So the current which is flowing here, it will always take the least resistance path. So all the current will flow through this circuit only. There will be no current which will flow here. Okay, because the both the terminal are shorted. They are at the same potential. So there are no current which will flow here in the this ohm resist. Okay. So that's why this current, the IN, so this 5 ohm will not come into a picture. The equivalent circuit will look like something which have this IN. And also what I have told here in this circuit, if you see, this is a voltage source. This is simply the 5 ohm resistor in series with a 5 volt. So you can convert this into a current source also. So this upper terminal is positive, so current will look like something like this. So the what is the value of current? I will be equal to V by R. V, what is the value of V? 5. And the ohm means voltage is there. Voltage is also 5. So it will come out to be 1 amps, and also the one resistor in parallel, that is equal to same as a 5 ohm. Okay. Now if you see this 5 ohm also it coming into the parallel of this circuit. So let's draw the 5 ohm here. Now how the circuit will look like? Circuit will look like something like this. 1 amps here, and this 5, what it become? It will become 2.5. Okay. And also in the upper part, if you see, the 2.5 was connected in series, and then one voltage source that was equal to 2.5 volt, and this path was short circuited, and where I have to find out the value of current, because the 5 ohm will not come into the picture because no current will flow into that. Okay. Let's apply the KVL here, KCL here. Let's take it as a grounded. Let me take another color here. Let me take the green. So suppose I have grounded here. So this voltage I am assuming this is a V, and applying KCL here. So what I have told, always assume that the current is moving out of that network. Okay. Here if you see the current is coming into the network. So that's why I have taken -1 plus V divided by 2.5.
Then
Any doubt?
you converted voltage source and resistor into
Yeah. So what I have done, I have converted this voltage source. If you see this voltage source, there is a one resistor in series. So what I have done, I have converted into the current source and one resistor in parallel. Okay. So this is became the equivalent circuit of this circuit basically. And this 5 ohm was coming into the parallel. So after this also, this whole circuit will convert into this 1 amps, because how to convert the current? 5 volt was the voltage and 5 ohm was the resistor. So 5 divided by 5, it became 1 amps. And this upper part is positive, so current will be, tip will be in the upward direction. And then 5 became 2.5 because they are in the parallel. So 5 multiplied by 5 divided by 10 is equal to 2.5. And then this circuit became simplified like this: 1 amps in parallel with 2.5 ohm, and this whole circuit in series with 2.5. Getting my point? Any doubt? And also here,
every time we convert the voltage source into
no,
current
no,
source,
not necessarily, not necessarily. But in this
we
course,
should write
yeah,
resistance in parallel with that current source.
yeah, you have to observe the circuit, how it could be simplified. I could have solved by the taking the directly the voltages and all, because I have applied the KVL here and try to solve. But the problem is that how to simplify that circuit. This circuit is much easier as compared to this circuit. But you can find it out. Okay. What is coming in your mind the first glance, you should try to solve it by that. Okay. Any doubt? Okay, let's move forward. Let's move forward. When you have
So that
uh,
voltage,
yeah,
after that, what we should do, sir, after that circuit diagram?
when you see the circuit, always try to that what is coming in your mind first head, and then try to solve it. Because in the network theorems, what happens that when you solve the multiple number of problems, multiple variety of problems, then each variety of problem will be in your head. Okay. Then after the solving lot of problems, when you get the problem now, you know the what category falls into that, in which category it could fall. Then you will try to solve by that. And this seeing from the first glance whether how to solve this circuit, this will come with the practice only. So I suggest you to use that means any book. The Sadiku is there. Sadiku is a very good book, and that can help you in the gate solving the gate problems as well. And it is from the basics. Okay,
What the book name, sir?
Sadiku. Sadiku is the author.
Voice is not clear, sir. Can you put a message?
Okay, let me see, and after that, let me solve this problem. After that, I will give the book name. Okay. So it will become V plus 2.5 divided by 2.5 is equal to 0. What is coming the voltage here? If you see, this will become minus 2.5 plus V plus 2.5. If you see here, the voltage is coming to 0 in this problem also. It means that this is at a 0 voltage. This is also a 0 voltage. This is also a 0 voltage. What current will flow in this circuit? No current will flow. Okay. So IN in this Norton equivalent is 0. Try to see once. After that, I will give any doubt in this. So I'm giving the link of the website itself. There is a one free PDF which is available on the site. Okay. So let me take the link. I'm sharing in the chat box. You can, okay, 2 amps. I'm sharing this PDF link. You can see that this is actually the Sadiku book. You can download it and try to solve the multiple problems from that. Okay. And this is older version. If you wanted to buy a new one, try to bring this newer version basically. Okay.
Yes, sir.
Okay. Let me go to the Laplace transform, which is actually which I wanted to give glimpse of something. So this is actually the in the few of the problems which is there in the assignment 6 basically. There is a you need to have know the knowledge of the Laplace transform. Okay. So Laplace transform means there is a one functionality that when you have the a function in the time domain ft, you can convert that function into the s domain. That usually make the simple analysis simpler. Okay. So how to go into the S domain? There is a rule that Fs is equal to 0 to infinity ft what was there in the time domain function multiplied by e to the power minus st dt and then integrate it. Okay. So this is a kind of, and it is if it a function means time is between 0 to infinity, it is being defined as like this. So let's take the one example. Let's take the unity function. Suppose I'm taking the unity function here. It is 0. How the unity function is defined? Ut is equal to 1 t greater than or equal to 0 and it is 0 when t is less than 0. Okay. So let's put in this formula and then try to see that okay, what is the value of fs for this unity function. So what is saying that it is 0 less than 0. After that 0 to 1, 0 to infinity, ft is 1 and e to the power minus st dt. Let's try to solve it. E to the power minus st divided by minus s, that is the integration of that, and then 0 to infinity. Put the value, you will get this is 0 minus e to the power 0 means minus 1 divided by minus s, it will be equal to 1 by s. Okay. So if the ft is equal to unity function, its Laplace will be equal to 1 by s. Okay. Similarly, let's take the delta function. If you take the delta function, so delta function is usually defined as a terminal, means zero values only. And one thing also I have told in this question means when we are solving some of the problem, g is to 0 to infinity, e means delta t, e to the power minus st dt. In that problem, I have told if it is delta t minus 0, so put that value here in the time domain, you will get the exactly that value, delta 0. So 0 to infinity, it will become, when you put this, delta t dt will be equal to 1. Previously also I have given this theorem, means let me here show you that f t minus t naught sorry, delta t minus t naught ft dt something, let's take to a to b. Okay, if t naught is lying between a and b, this integral will become something like this: a to the b. Sorry, this value will become f t naught. If it is not lying in between, t naught does not belong in between the a and b, then the function will, this integral will become zero. This theorem, which I have told in the last tutorial session itself. Okay, so there are few of the formulas related to that. When whether it is a ramp function, whether it is a delta function, whether it is different function kind of functions and all. So there are standard. You can solve it by converting from that equation which I have told, that 0 to infinity ft e to the power minus st dt. But if suppose this is a function, this is a function. What is a function here? Ft is equal to t to the power n. What is the meaning of t to the power n? T square, t cube, t, t to the power 4. You can directly convert this into a this Laplace domain. It will be equal to n factorial divided by s to the power n plus 1. Suppose I am taking t square. What is the value of Laplace transform? It will be equal to 2 t square, suppose 2 factorial divided by s to the power 2 plus 1. It will be equal to 2 divided by s cube. Suppose I am taking t cube. What is the Laplace transform of this? 3 factorial divided by s to the power 3 plus 1. It will be equal to 3 multiplied by 2 divided by s power 4. It will be equal to 6 divided by s power 4. So like that, this first formula will be applicable. Okay. Second formula is related to e to the power 80. Suppose in the function e to the power 80 is given. So when you convert into the s domain, it will become 1 upon s minus a. Similarly, if you have minus 80, e to the power minus 80, it will become 1 upon s plus a. That is simple. Okay, getting my point. So this is actually the, when you integrate e to the power 80, e to the power minus st dt, so Laplace transform of t to the power n will be equal to this. Laplace transform of e to the power 80 will be equal to this. Similarly, sine, when you take sine of bt, kind of when you take the Laplace transform, it will become b divided by s square plus b square. Same cos, when you take in the cos, at the end s is coming, so upward in the numerator s is there. Okay, this is trick to learn whether when it is sine or the cos. So this is kind of s divided by s square plus b square, and sine bt b divided by s square plus b square. Okay, so this is the few formula you should remember while trying to solve the problems. Okay, let me take you one problem which is easier, but how to solve that? Okay, suppose this is the first problem given ft, and you have to solve what is the value of this is first problem and this is second. So let's try to find out the Laplace transform of the first function. Ft is given as t square minus t minus sine 2t plus e to the power 3t. Suppose this is t square, no? So t square will become 2 factorial divided by s to the power 2 plus 1 minus t to the power 1 is there, so 1 factorial divided by s to the power 1 plus 1. What about the sine bt? Sine bt is b divided by s square plus b square. B square means 4. What is the power e to the power 80? It will become 1 upon s minus a, s minus 3. What will be the Laplace transform of this? 2 divided by s cube minus 1 divided by s square minus 2 divided by s to the s square plus 4 plus 1 upon s minus 3. So this is actually the answer of this problem. Okay. Any doubt? Just remember the formulas. Okay. Applicability I am showing how to use that. Okay, so let's take the another example. This example 2. This theorem, this means Laplace transform is nowhere easy to solve or grasp. You have to see the book and you have to go through the lecture for understanding. Okay, so let me take this second example what I am telling you. If you see the second problem, it is a one graph is given. Graph, this value is 1, this is 5. So fundamental equation is Laplace transform of ft, any function of t will be equal to 0 to infinity e to the power minus st means ft e to the power minus st dt. So when you see in this problem, it is a piecewise function. Piecewise function is there. So in between 0 to 1, it is 0, 0 e to the power minus st dt plus in between 1 to 3, its value is 1 e to the power minus st dt plus when you see from this is actually suppose this is actually 3, 0 here, 1 here, 2 here, 3 here, 0 to 1 to 2, it's a 1 st, and then after that if you see 2 to 3, it's a 0 e to the power minus st dt plus 3 to 4, it's a 5 e to the power minus st plus 4 to 5, it's a 0 e to the power minus st dt and so on. Okay, let's try to solve. This is 0 here, so it will become 0. Plus here, if you see e to the power minus st, so what is the integral? E to the power minus st divided by minus s, and then put the value 1 to 2 plus here also 0, 0 plus here if you see the 5, so e to the power minus st divided by minus s, put the value 3 to 4 plus this is also 0. So this is actually the solution of this problem. Okay. So when the things are given in the Laplace domain, time domain, you can convert into the Laplace domain for the analysis. Let's take the another problem which is there in the bottom, that is inverse Laplace. When you see this problem, it is given in the S domain and it is asking what is the value of ft. So it means that when you convert from ft to fs domain, then you can also from fs to ft you can convert by the same theorem. Okay. So let's see. So what I have told in the cos bt, if the cos bt is a function, what is Laplace transform? S divided by s square plus b square. When you see in this question, it is also in the similar form, s divided by s square plus 4 square. So it is basically the cos 4t. What about this? This is actually 2 e to the power minus 3t plus 3t. Because e to the power 80, what is the Laplace transform? 1 upon s minus a. That is similar form, 2 e to the power minus 3t. And what about the s plus 1 by s cube? It can be converted into the 1 upon s square plus 1 upon s cube. So if it is a t square, a t, then it become 1 factorial divided by s power 1 plus 1, that is s power 2. So it is the same, that is t. When you about what about the t square? It is actually the 2 factorial divided by s to the power 2 plus 1, that is cube. So it will what about 1 upon s cube? It will become t square by 2 factorial, that is t square by 2. Okay, so you have to remember the formulas what are there and you have to solve based upon that. So let me take what is the actually the question was there. So let me take a new slide. Give me 2 minutes. I will not take much time. In the question it is given some of the like this kind of a plus b t e to the power minus 80 kind of equation is given, and one circuit was given something like this kind of, and in the question it was asked what is the Thevenin voltage. Okay, and this ft is the voltage source or something, vth was given. Okay, so in that problem you have to convert into the s domain and then the see the what is the coming the values, then you have to convert into the t domain. There you have to find out the a b value and the tau value. Okay, in that questions you have to solve by seeing in the S domain, then convert into the T domain, and then you will, when you see the assignment problem, you will get the feel. So what I have told in the lecture itself, two things, what is the network theorems are there. Second, I have told about the Laplace domain. And one doubt, one thing which I have not said correctly, that is about that Telenga's theorem that I wanted to explain what was the correct form. let me take one other slide. There was one error which I have told. Sorry, compensation theorem basically. So in the compensation theorem, what I have told, so if you have the network, suppose this is a network V and a voltage source, and there was one network, and there was one resistor as there, and it was asking, and the current which was flowing initially was something like this, and this was the value of R. Okay, and when you say that, and this R is converted into the R dash, then it is asking what is the value of delta I, current change basically. What was the initial, what was the final? What the about the compensation theorem says that same the voltage source here, network will be here only, and the same what I have told here, the you have to replace the R new. R new matlab R dash and one voltage source in between, and this voltage will be equal to I which was flowing initially, and the voltage multiplied by delta Z. Delta Z, what is the value of delta Z here? R dash minus R. And the current which you get here, that will be delta I basically. That is the change of current, change in current. Okay, for finding out the value of new, that is delta I will be I new minus I old. So I, what was the I old? It was I only. So I new, you will get the delta I by this from here. Then I will be equal to delta I new minus I delta I basically. So after converting from the that voltage source and in connection with the R dash, that the current when you get from this voltage source, that is actually the change in current, that delta I. In the assignments also, in the assignment 6, when you see the question, second question, there also it is was asking what is the change in current in the question itself. So you will get the feel that ki how to convert that. Okay. Any doubt in this?
No, sir.
Okay. Try to solve the assignment 6 problem, and if you face any doubt, we will clear it out in the other tutorial session. Also, try to ask with the other TAs also, so that you can get a better feel of that. Okay, try to ask them the questions, new question. Try to solve from the Sadiku and ask from the ask during the tutorial session. Okay. Okay, that's end for the today's tutorial session. I hope I have cleared most of the doubt and try to solve as many questions as possible. That is the only fundamental to clear the means get the feel how to solve the particular problem at a first instance. What to apply, when to apply, how to convert. Try to solve as many questions as possible. And if you feel any doubt, we will discuss in the next session. Okay. Okay, that's all from my side.